very basic introduction to just exactly what is a chemical equation. So first of all, before you can do a chemical equation, you got to know what is a chemical reaction. Well, it's any instance where a substance completely changes its identity. So like when you take a piece of paper and tear it in half, you still have paper. You didn't change its identity, so that was not a chemical reaction. But what we have here in the picture is this little zigzaggy thing right here. This is a piece of pure magnesium metal, and it is reacting with oxygen in the air to produce something that is very different. It is a completely different chemical known as magnesium oxide, and you can kind of see the atomic representation of it here, and then this is what we are ultimately working towards your chemical equation. Just some vocabulary. The reactant is what you start with. The reactant reacts and the product gets produced. So the product is what results from the chemical reaction. And all chemical reactions do follow the law of conservation of mass, which basically means that the total mass of all of the reactants is going to equal the total mass of all the products. You cannot create or destroy mass. If you figure out how to do that, then I'm pretty sure a Nobel Prize in Physics is coming your way. Because 500 years worth of physics, no one's been able to do that. But so a chemical equation, which is this guy right here, this is an equation. You can see we got plus signs, and we don't really use equal signs so much in chemistry. We use arrows. But basically what the chemical equation does is it represents the identities of the chemicals involved and relative amounts. And this is very, very important and will be important throughout the entire rest of the year. So I'm going to try to make sure that I explain this very, very clearly. So you use symbols and formulas to represent your chemicals. So here you see that we have the element magnesium. Here we have a compound of oxygen, and I'll explain why oxygen is paired up like this. I can't remember if it's in these notes or if it's in another set of notes, but I'll explain why at some point. And then here we have the formula for the compound magnesium oxide. Now, I'm not going to teach you guys how to write formulas in these notes. So if you need a refresher course on how to write a formula, then you need to go back and watch the Writing Chemical Formulas notes. And then you're going to use something called a coefficient to balance the amounts and make sure that however much products you have is the same as the, I'm sorry, I said that backwards. How many reactants you have is the same as the amount of products. And so the coefficient, and I know that I'm whiting and right, so you can't see that, so let me change colors here. So the coefficient is this big number out front, and it applies to any compound that comes after it. So this too applies to the magnesium. In front of the oxygen, there is no number, and so that just means that we assume that it's a 1. But chemists get kind of lazy and they don't write 1s. It's kind of superfluous anyway, so don't write a 1. If there's no number out front, then it is assumed to be a 1. And then this 2 applies to both the magnesium and the oxygen. And to show you that this is balanced, you can see that we have 2 magnesiums, and over on the product side you have 2 magnesiums. Here we have 2 oxygens, it's 2 oxygens bonded together, and over on the product side we also have 2 oxygens. And then you can check law of conservation of mass here, showing you that they add up to be the same. So how do you know if you've had a chemical reaction? Well, if all of a sudden your substance gets really hot, or flips out of that really cold, or it releases some form of light, that's a dead giveaway that you've had a chemical reaction. If all these bubbles start showing up and you didn't just shake up a soda, if like you put one chemical into another chemical and then bubbles just magically appeared, then that is also a hint for a chemical reaction. The formation of a precipitate, and I'm going to talk about this later, but you have this picture here and you see that there is a clear liquid up here, and then there's a clear liquid down here in your Erlenmeyer flask. But when you mix these 2 clear liquids, you get this yellow solid down here, and this solid that's produced is the precipitate. So a precipitate is any solid that is produced from the chemical reaction of 2 aqueous substances. And then if something changes color, that could be indication of a chemical reaction. It could also not be. Color change is one of those things that you really want to make sure that if you're going to, say that something is a chemical reaction, that you have more than just a color change. That's like saying, oh, okay, I'm going to look at a person with long hair and say that, well, that person has long hair, so that's a girl. Well, no, not necessarily, because guys can have long hair. Flip side of that, oh, that person with short hair, that's a guy. Well, no, not necessarily. You definitely want to look at other factors. So if you had color change in combination with, say, the formation of a gas, well, then that would be evidence of a chemical reaction. A word equation is something that you can use if you want to. I tend to make more use of like underlining instead of word equations. But a word equation, and once we get to actually writing out reactions, I'll show you what a word equation is. But basically, it can act as a bridge between the big, overly worded word problem and then the actual concise chemical equation. But like I said, I don't use these too much, but if they help you keep track of what you're working with, then most definitely make use of them. So how to write elements. Well, you would think, well, an element, just look at the periodic table and write it down. Well, you would be right. Most pure elements are written as the elemental symbol that you find on the periodic table. But just like every single rule that you will ever encounter in your life, there are exceptions. The biggest exception is the diatomic molecules, and they include Brinkelhoff. And basically, it's a molecule that contains two identical atoms, and Brinkelhoff are the elements that do it. You can kind of call it Brinkelhoffit, but astatine doesn't really react too awful much, so we kind of typically just ignore that little guy there. But these are the elements that, when they exist in their pure state, they don't exist by themselves. They have to exist paired up with another of the same atom. So like before in that reaction when I showed you that O2, oxygen, pure oxygen is written as O2 and not just O, well, that's because oxygen is a Brinkelhoff twin. And maybe you're wondering, well, why would they go through this problem of pairing up to begin with? Well, it has to do with stability. Oxygen by itself, it has 6 valence electrons. And this by itself, it's not really that stable. But if you can get 2 oxygens to pair up, you learn how to draw these with the Lewis structures. This is a more stable situation than this. And so these elements are all more stable when they are paired up than when they're by themselves. And you guys learned a long time ago that nature prefers things easy. And so it's going to take the most stable route. Just to show you one more, fluorine. Fluorine typically has 7 valence electrons. Look at the periodic table if you don't remember how to do that. And a fluorine by itself looks like this. 2 fluorines bonded together looks like this. And this is a more stable, and kind of can't see that dot right there. This is a more stable situation than this, because this enables both fluorines to have a full outer octet, which makes all elements happy. Same thing here. Now, whether or not it's single or double bonds is entirely dependent on what those particular elements need to satisfy the octet rule. And again, to refresh your memory on that, you can go back and watch the Lewis structures video. And there are some other really crazy exceptions. Sulfur actually does this wicked 8 pairing thingy that looks like that. And then phosphorus pairs up by 4s, and it looks like that. All that I expect you guys to know is that, I do not expect you guys to know these shapes, but I do expect y'all to know that sulfur, when it's by itself, is actually S8, and phosphorus, when it's by itself, is actually P4. Alright, so the symbols that you'll see used in the equations, well, the biggest one that you'll see is the arrow, and the arrow means yields. Basically, it means that the reactants turn into the products. In this class, we'll kind of focus on this unidirectional arrow here, but if you guys take AP or if you take higher level chemistries, you will learn that actually most reactions are reversible. And in that the reactants, whatever is written on the left side, is turning into the products, whatever's written on the right side, but then it can also go back the other direction. But again, we're going to focus in this, in general chem, in this first level chemistry, on unidirectional. We're just going to focus on turning reactants into products. Then you can have little symbols written above the arrow. If you have a triangle, so like if this was our arrow and we put a little triangle over the top of it, well, that would mean that we applied heat to that particular equation. Maybe the reaction needed some heat to get it going. If we put a specific compound or an element, then that means that that compound or element was used as a catalyst, and I'm sure you guys remember catalysts from biology. It's just a chemical species that participates in the reaction to speed it up, but doesn't actually get used up itself in the reaction. Like, you put it into the reaction, and then at the end of it, you can pull out that catalyst. It's, it wasn't, the catalyst wasn't permanently chemically changed in any way. If there is a specific temperature written above the arrow, then that means that that particular reaction has to occur at a specific temperature. And same thing with the specific pressure. Then you can have things written after a formula. These are pretty self-explanatory. If you have S written in parentheses, and that means you're dealing with a solid. L written in parentheses means you're dealing with a liquid. AQ stands for aqueous, which just means that it's dissolved in water or that it's a solution. And then G obviously stands for gas. So, we've got a couple of examples I wanted you guys to do. So the first example, solid sodium oxide. So actually I'm going to switch back to white because I think y'all can read that better. Solid sodium oxide, and this is what I was talking about with underlining and what instead of doing the word equation. Sodium oxide is added to, so I'm going to get rid of all that and swap it out for a plus sign, to water. So water is my next one. At room temperature, if this is at room temperature, equations are generally assumed to occur at room temperature unless otherwise noted. And forms, so I'm going to swap out and forms with an arrow, and then the product is here sodium hydroxide. So I'm going to write the formula for sodium oxide. Sodium is in group 1, so it's a +1 ion. Oxide is in group 16, so it's a -2 ion. Crisscross those and you get the formula Na2O. And then the question said it was a solid, so solid. And then is added to plus water. Well, that's H2O. What state is our water in? Well, they told us that all this is happening at room temperature. Well, at room temperature, water is a liquid. And forms sodium hydroxide. Well, again, sodium is a +1. Hydroxide is the polyatomic ion OH with a -1 charge. And so they're just going to naturally come together, NaOH. And for the state on this one, we had a solid plus water. Well, the water here is going to cause this guy to be, whoopsie, I forgot my A, aqueous, because anything dissolved in water is aqueous. Now, I know that this reaction is not balanced. I will show you guys how to balance later, but this is what the reaction would look like. One more example, and then we will call this one quits. Ammonia is produced by, so is produced by means that ammonia is the product reacting excess nitrogen with hydrogen. So, nitrogen plus hydrogen yields ammonia. Well, nitrogen is an N, and they did not indicate a physical state for this reaction. And when a physical state is not indicated, then you can assume it's at typical lab conditions. So, room temperature, 1 atmosphere of pressure. Now, if you guys remember, nitrogen is part of Brinkelhoff. So whenever you have pure nitrogen, it pairs up. And if you look at the periodic table, you can see that nitrogen at room temperature is a gas. And then we're going to add that to hydrogen. Hydrogen is also part of Brinkelhoff, so it's going to be H2. And hydrogen at room temperature is a gas. I'll give you a hint, a gas plus a gas. What do you think it turns into? Now, ammonia is one of those compounds like water where you should know the common name. The common name, ammonia, represents the formula NH3. And because we had a gas and a gas, if you guessed that we're going to be making a gas, then you guessed correctly. Yay for you. Again, I know that this is not balanced. I will show you how to balance reactions in another set of notes, but I just wanted to show you what a reaction looks like. And that, ladies and gents, is all I have for you.